This is a brief report on the Columbia Space Shuttle disaster which occurred in 2003. On January 16, 2003, after being delayed for over 2 years, the Space Shuttle Columbia was made ready to launch from Kennedy Space Center. Its 7 crew members boarded, between them over 4,800 hours of training to handle the spacecraft, and an additional 3,500 hours to handle the payload for the coming mission. After months of delays, the shuttle was finally cleared for flight. The massive fuel tanks filled with liquid hydrogen burned their contents to ensure that the small skyscraper of the orbiter shuttle reached the heavens. Engines roaring, smoke blaring, the machine took flight. Flying at nearly 1626 miles per hour, the shuttle soared, flying high into the upper atmosphere and beyond. But something happened at around 66,000 feet. Amidst the high acceleration and increasingly frigid temperatures of the upper atmosphere, a piece of foam attached at the bipod holding the external fuel tank in place broke off. Nearly the size of a suitcase, the insulating foam block sheared off from its place and slammed into the shuttle's wing. Unbeknownst to the crew or ground control at the time, the impact damaged thermal protection tiles on the left wing, creating a small breach. Heedless, the shuttle continued on its way, settling into its flight path and preparing for its 16-day mission. The impact of the foam is the longest and most commonly cited cause for the Columbia disaster. But that alone does not explain what happened. Since the 1970s, the NASA budget was in steady decline, but the desire to continually improve aerospace technology continued. NASA was eager to design a reusable shuttlecraft that could make routine space flights for both commercial and military purposes. However, due to the budgetary constraints at the time and the need for the shuttle to carry large dimensions of cargo, the spacecraft design was necessarily compromised. Most noticeably absent from this design was the lack of means for the crew to escape the aircraft. This exclusion was brought about primarily due to the designer's complacent belief that the craft they designed would be safer than any previously manufactured. Still, perhaps the greatest compromise that was made in the design of the orbiter shuttlecraft was between the original ideation of the shuttle and its actual state. The shuttle that was promised was one that could be launched at a moment's notice, making many trips to and from space over the course of a year. This image that was touted at its inception of routine spaceflight has caused experts to overestimate the safety and reliability of the craft over the years and lead to greater complacency. This act of compromise carried NASA throughout its operations as its budget continued to dwindle, whilst the number of programs and obligations it maintained continued to increase. The budgetary issues of NASA were well known at the time, but were exacerbated by NASA's workplace culture. NASA's ethos was that there were inherent risks in the work they did, which had to be accepted but could be overcome through the determination, efforts, and high quality of its workforce. However, this led to a degree of overconfidence in the abilities and decisions of its members, and made them resistant to reviews and changes exerted by external agencies. With the continued budgetary constraints and the low workforce, NASA could not work to construct a newer, more advanced shuttlecraft. In fact, much of the infrastructure that was built in the 1970s was still being used by the early 2000s, well beyond its expected operational lifespan. This is a problem because operational expectations cannot really be met without updating a 30-year-old infrastructure. Yet still, the NASA's ethos of Canada kept it going even as it took on more and more contract work for its space flights to maintain operating costs. Which leads to the sustained issue of the foam insulator. Prior to the flight, foam insulation is sprayed over the exterior of fuel tanks. Ironically, this is done to prevent the fuel tanks from being covered in ice, which might break off during takeoff and cause debris damage to the shuttle. The portion that broke off, however, was a large piece of foam attached at the bipod connection between the shuttle and the fuel tanks to prevent any freezing of the tanks from affecting the shuttle proper. The issue of foam shedding was well known and had been seen in a number of other previous flights. It was even common for small popcorn-sized pieces of foam to pop off during takeoff and leave minor damage in some thermal protection tiles, which would need to be replaced. The view of the damages caused by the foam was increasingly accepted as more and more flights returned with damage that was attributable to the foam shedding, and came to be seen with complacency as an unavoidable hazard. Instead of being something that might lead to an incident, its continued presence was viewed instead as necessary turnaround in getting a shuttle ready for another flight. We begin to see, at least in regards to the foam, that due to the budgetary and workforce constraints, a potential problem that could have been addressed were disregarded. as well as how the workplace culture of NASA and the lack of major incidents previously lead to a lower risk assessment of the potential hazard the foam presented. Furthermore, the Columbia mission was situated within a fairly tight area for mission operation timelines. The time constraints on future projects may have imposed additional costs on the decision-makers to ignore what was decided to be a continuous minor nuisance of foam impacts and push for the continuation of the already delayed Columbia launch. It wasn't until day 2 of the mission, as the footage of the launch was being reviewed, that the anomaly at 81 seconds into launch was detected. While this was done at multiple review stations, the size and severity of the impact was difficult to ascertain, in part due to the low quality or lack of footage available. While there may have been additional ground footage revealing the potential separation of foam from the tank, it was not sought after as a means to provide greater context to the accident. Investigation. This was another perennial issue with the NASA flight systems, as budget cuts and lack of interest on the part of the organization for improving or building upon existing shuttlecraft designs allowed the cameras to fall into disrepair and malfunction in their tracking of the craft. While initial reports held that it was something that wasn't worth looking at over the holiday weekend, engineers from Boeing persisted anyway, analyzing the footage. They were surprisingly accurate in their projections of the size and impact of the foam as it struck the underside of the left wing at nearly 500 miles per hour. The damage assessment in this case was compromised by the limited predictive models that were available. While multiple models were run both in and out of house, they were largely discounted as being inaccurate. Indeed, the predicted impacts for some of the analysis would have meant a complete breach through the tiles, which had never happened before due to foam. Compounding this uncertainty was that many of the models used for large-scale impacts were tested and calibrated based off of ice impacts rather than foam-based debris. These previous models were also known to overestimate the actual damage, leading to distrust in the initial models and guesswork about the potential consequences. Later presentation of this information at future decision-making junctions never discussed the sheer uncertainty and guesswork involved, resulting in an unwarranted perception of confidence in the subsequent decisions. Still, the debris assessment team submitted a formal request to the Department of Defense for further imaging. Unfortunately, this request was mistakenly cancelled by one of the program managers, who did not understand where the request came from and was unable to communicate to the team who requested it why the request was denied. Even as more requests for imaging were sought out, they were ultimately ignored, downplayed, or refused as the initial assessment was circulated. Program managers were overly optimistic about the impact and held to the expected narrative of no flight hazards due to foam debris, as there never had been before. Breaks in communication led to questions and cancellations where action was needed. When concerns persisted, they were downplayed and placated that if there was a breach, then there was nothing that could be done anyway. Once more playing into the NASA's culture of acceptable risk. And so at 9 a.m. on February 2, 2003, the Columbia crew was cleared to deorbit and enter the atmosphere in a controlled burn. During the heat of re-entry, there was less than a minute between the alarms going off indicating a critical malfunction as the wing sheared off and the depressurization of the cabin. Without the problem being identified and rectified prior to re-entry, there was nothing that could be done. The astronauts were never made aware of the issue, and no efforts were made to create a plan that would have allowed the impact site to be fixed. Columbia exploded, killing all 7 astronauts and scattering. While the issue with the foam could have been explored and resolved much earlier, the complacency of it continually damaging shuttlecraft addressed the foam blocks on the bipod redesigned and the camera operators made to actually do their jobs. But this did not happen. The realistic extent of the damage could have been more accurately communicated. The request for visualization could have gone through and a plan for repair implemented. But this did not happen. At many points, something could have been done to prevent or resolve this damage, but ultimately this did not happen. We also have to keep in mind that previous successful flights included necessary stringent material testing and safety issues that were tested for, and they had passed. It seems that because these forefront safety issues were met, experts didn't think it was necessary to add additional safety features that we as human factor students would think are needed, like building a safety escape route. As in this scenario, even today there seems to be an easy disconnect between scientists' needs for operational success and the funding committee's understanding or complacent understanding between what is required and what is needed. It is imperative that there is a team who can accurately, visually, and clearly convey the safety team's request to be proposed to the funding committee in a way that they will understand. Safety can't be met with a bare minimum, but not is not an obvious statement. Though the message in this visual is very clear, and something like this won't be shown to a funding committee, you can get the idea that money is needed or people will die. The safety committee and human factors personnel must work with other teams to make sure that the person presenting the mission's proposal clearly, and even more importantly, other teams must learn to be receptive to the safety committee and human factors comments and recommendations. This incident displays the importance of establishing clear lines of communication within an organization, as well as the need to not grow complacent or accept turnaround damages as normal. By establishing an efficient system for communication requests and making that well known, as well as providing realistic scenarios and the need for greater information, disasters such as these can be averted. That's the end of our presentation. Thank you for listening.